Okay, so last thing that we talked about, if I remember, was the capillary, right? So now I'm going to introduce you to phase transitions. You guys are familiar with phase transitions? Yes, no, maybe?
Yeah.
Good. So it should be real easy. Where's your sister?
She wasn't there in the morning?
No, your sister was there in the morning, but I was talking about Angelia.
I don't know. I'm not at home right now, so.
Okay. Okay, so what are the phases? Do you guys remember some of the phases?
No, that's the states are solid, liquid,
Or the states, yeah, exactly. Solid, liquid, and what?
vapor. No, what is gas?
Paper? Solid, liquid, and paper. Is that the other state?
No, I thought I was gonna say vapor, but I'm like, no, it's not.
You mean gas, right? Vapor will be fine, but it's gas. That's what we typically go with, right? So phase transitions are the changing from one state to another state. So if we're going from a solid to a liquid, that's melting, right? Nothing fancy, just called melting. It's also called fusion. If we're going from a liquid to a gas, that's called vaporization or evaporation. If we're going from a gas to a gas to a liquid, that's called condensation. If we go from a liquid to a solid, that's freezing. Okay, so we also have phases where we actually skip that middle one. So we go straight from a solid to a gas, sublimation. And if we go straight from a gas to a solid, deposition. Okay. Now, the fact that it goes in both directions, right? So like here, you have the arrow going in one direction and also going in the other direction. So these arrows kind of represent what we call dynamic equilibrium. And so basically meaning that you could have both of these phases existing at the same time, right? And so when they reach dynamic equilibrium, the rate, let's say if we're talking about melting and freezing, the rate of freezing is going to be equal to the rate of melting. So in other words, if it's reached dynamic equilibrium, you have molecules that are going at the same rate in both directions so that you're maintaining that state, okay? So like for instance, if we had a lake full of water, this is my pink lake, okay? Now, there's vapor above the water. And so if we're in a closed atmosphere and we allow time to take place, then the amount of water molecules going up into the vapor phase is going to be equal to the amount of water that is condensing back down to the liquid phase. Okay, you guys kind of get that, give or take?
Yeah.
Yeah, kind of.
Okay. Let's see. I'm trying to think. Okay, so the thing about your phases are also gonna be affected by intermolecular forces, right? So for instance, vapor pressure, and vapor pressure is just the pressure associated with the vapor, okay? So vapor pressure is going to be directly influenced by intermolecular forces. So the weaker your molecular forces, the higher the vapor pressure is going to be. The stronger the molecular forces, the lower the vapor pressure is going to be. Now, the reason that is because if it's a strong force that's kind of keeping everything together, then it's going to remain in the liquid phase, right? You're going to have a lot more of it in the liquid phase and only a little bit of it in the vapor phase. But if you have a lot of weak forces, I mean, you just blow on it and it kind of goes up into the vapor phase, right? So because the forces are so weak, not keeping it together. Does that make sense? As well?
Yeah.
Would that be like dried ice?
Yes, dried ice is a good example. So you're literally going, it's sublimation. You're going from a solid to a gas. And just because those forces are so weak, you know, just because it's only interacting through dispersion forces, and that's the weakest force, it just literally goes from solid to a gas. It even skips over the liquid phase because it's so weak, you know. Where water, you know, it goes from that ice to a liquid and then to a gas because it has hydrogen bonds, which are stronger intermolecular forces. Okay. Okay, so after a vapor pressure reaches equilibrium, the number of molecules that are going into the gas phase aren't going to change. So ultimately, the number that are there in that gas phase are going to stay consistent, and that's part of reaching that equilibrium state. So the external pressure that's placed on vapor over liquid is going to remain constant. That's going to be in a closed system. Okay. And then again, this is going to be strongly influenced by intermolecular forces. And this is just an example. So if we look here, so we put a liquid into this closed system here, closed container. And then initially the pressure on the container is 0. Over time, as the system gets all warmed up and it gets into its equilibrium state, or gradually as it's going into or towards its equilibrium state, pressure starts building up. So you start to see an increase in pressure. Then over time, it reaches a state of equilibrium. Once it reaches a state of equilibrium, that's when you're going to get your actual vapor pressure. Now, this vapor pressure is going to be consistent at certain temperatures. And it's also going to be dependent on temperatures because you guys remember, we'll go PV equals nRT, and vapor is a gas, right? So as temperature goes up, our pressure is going to go up, okay? And then also we know that what happens when we heat things up, molecules move faster. So a lot of those molecules are going to be moving and releasing from the liquid, right? And so, but again, if it's held at a constant temperature, you're going to have a constant pressure that's going to be associated. Does that make sense?
Yeah.
Or is it just like black box? Okay, good. So now I have a question for you. I want you guys to take about 10 minutes to sit there and think about it. There's only one of you. There's only 4 of you here. So we'll just keep you guys together and let you guys think and talk together. I'll go grab something that has caffeine in it, but don't pass out on you. But here's the question. Given the shown structure formulas for the 4 compounds, explain their relative vapor pressure in terms of types, extent of IMS, and intermolecular forces. Okay, so here's your different molecules. We have ethanol, we have ethylene glycol, we have diethyl ether, and we have water. So what I'd like you guys to do is put them in order. The one from the lowest vapor pressure to the highest vapor pressure, and then also be able to explain why you think the one that is the lowest vapor pressure is the lowest vapor pressure, and why you think that one that's the highest vapor pressure is the highest vapor pressure. Does that make sense?
Yeah.
And you guys should kind of get used to this because these are all like concept questions. You notice we haven't done real math in a long time. Like there's only been like one real math question, right? So a lot of this is just concept. So you want to make sure that you're thinking about these concepts. Okay. So I'll leave you guys to it. I'm going to find a drink. Hopefully something good with caffeine. I'll be right back.
So what do you guys think?
I think water has the lowest vapor pressure. That's for sure. I mean,
Why? You said right to explain why.
yeah, because it has the strongest. Well, from what I see, it has the strongest intermolecular forces. Forces.
Oh yeah, because it's gonna have to go through the if it's in the solid, it would have to go through the liquid and then to the gas phase. It can't just go from a solid to a gas phase.
So you think it's the strongest? No, right? Or no.
Yeah. Well, yeah. I think it has the strongest intermolecular force. Therefore, it has the
It's the
lowest vapor pressure.
Yeah, the lowest we could, or the lowest vapor pressure.
Mm, the lowest. No. I don't know. Do you guys know like exactly like how you're supposed to figure it out? I feel like the way that what is it, diethyl ether? Like the way it's bonded might be like the highest. The way they're like bonded together might make it the highest vapor pressure. I don't know. Maybe I'm tired and kind of just talking.
No, well, yeah, you might be onto something now that I'm looking at it
Yeah,
more.
I think that's the highest vapor pressure because there's no it looks like to me it's the what is it, dispersion forces or intermolecular forces or London forces, which is the weakest.
Oh, okay, okay.
Like, you know what I mean?
Yeah, I see what you mean.
Then I think the second lowest vapor pressure would be the ethanol glycol. Because that
Why?
one has, huh?
Oh, go on. I was gonna ask why, but you were about to explain it. Sorry. I apologize.
It looks like because that one has both hydrogen bonds and London or dispersion forces. And the hydrogen bonds are pretty strong intermolecular force, you know?
Oh,
I don't know.
yeah.
I could be wrong. Because ethanol has one hydrogen bond right there too.
Well, it doesn't have to.
Ethanol?
Oh no, I was talking about ethanol glycol.
Oh yeah. Ethanol glycol does. That's what I was gonna say. That's the second lowest vapor pressure, but I don't know.
Mm, I'm confused.
You want me to leave again? Should I go?
We
Well,
almost
Yeah. So like we're understanding that like we gotta like find the intramolecular force to determine like what's the strongest, what's the weakest. But like we're having trouble like categorizing each one and what intramolecular force it is.
Mhm.
Maybe it'll help if you kind of write out the intermolecular forces. It may help you think about which ones are acting. I'm just saying.
Like write out the intermolecular force, but that's what we're having trouble like figuring out.
Which ones are there?
Uh you were talking a lot about the London one.
Okay.
the dispersion forces, hydrogen bonding, dipole, or ion dipole.
Okay. So let's figure out, are there any ions here? What is the definition of an ion?
OH ion.
OH is an ion? Are you sure? What is the definition of an ion?
Or gaining electrons.
So it's something who's gained an electron or who's lost an electron, right? So it has to have positive and negative charge associated with it. So a cation, an anion, remember?
Yeah.
And it's typically usually a metal and a non-metal. You see any metals on the screen?
No.
So we have no ionic compounds there at all. You can kind of give up the ion dipole and those mixed characteristics, right? But we can have dipole, right? Because dipole basically means that you're working with the formation of dipoles. These are all covalently bonded compounds, right? Yes,
Yes.
no, maybe? Okay,
Yeah.
so if they're all covalently bonded compounds, the only thing that they can do, they can either form dipole, they can form hydrogen bonding, they can form London forces. So you have three that you're working with. Or dispersionary forces, same difference. Because you're talking about the compounds as pure compounds. You're not talking about them as they interact with each other. So pure wise, right? That makes sense? Okay. So knowing that, what forces do we have acting on ethanol?
Would it be dispersion forces and hydrogen bonding?
That's right. So the pink, that's going to be dispersion. The blue, that guy's going to be making hydrogen bonds, right? Okay, what about ethylene glycol?
I know the hydroxide would be hydrogen bonding.
Okay,
I don't know
so
if
yeah.
that one.
And
I don't know
then-
if it's dispersion forces or dipole. I get confused by the two sometimes.
So dispersionary forces are basically anytime that you see hydrocarbons, they're going to be dispersionary forces. Anything that doesn't have, that won't have polarity naturally on their own are going to be dispersion forces. And even polar molecules have dispersion forces. So, but they're typically very weak, and they're like, since they're so weak compared to the other force kind of takes over. So in this case, you have two, right? You have, again, these guys are going to form your hydrogen bonds. And then these guys here are going to form dispersionary forces, right? Now, when we talk about dipole is basically you have something that is slightly electronegative and something paired up with something that's less electronegative than it is. So like if we did sulfur and chloride, right? So sulfur is less electronegative than the chloride. And so the electrons are going towards the chloride. So then that gives this guy a slightly positive charge. And this guy gives it a slightly negative charge. So that would be dipole-dipole. Now that differs from the hydrogen bond, because there's a huge gap between the hydrogen and the oxygen, and there's a huge gap between hydrogen and fluorine and hydrogen and nitrogen, that those bonds are going to be stronger. I mean, the hydrogen bond is going to be a stronger force in that case. It's still dipole-dipole, but it's a much stronger dipole-dipole. Does that make sense?
Yeah.
Okay. Okay, and so we can kind of get rid of dipole-dipole because there's not going to be too much dipole-dipole going on because these guys are going to be kind of occupied with the outer part of it. Now, what about this guy here?
Isn't that dispersion forces too?
This one is just going to be dispersion forces. And then water.
Hydrogen bond.
Okay. Now, knowing that, what's going to be the order?
Water would be, you said lowest vapor to highest vapor, right?
That's right.
Pressure. So would it water be the lowest?
Nope. Okay, now think about it. Water has two places where it can form hydrogen bonds, right? It could be with that OH, it could be with that OH. This guy also has two places where it can form hydrogen bonds. Plus, it also has dispersionary forces. The dispersionary forces are an additive, right? They're just like adding on. The more forces that you have acting on it, the stronger it's going to be. So which one is going to have the lowest vapor pressure?
Ethanol glycol.
Okay. Let me type it. It's my handwriting. Does that make sense?
Yes.
Wait, so like the so is like the highest intermolecular force the highest vapor pressure too, or?
No. Okay, so you have to think about the forces as strength, right? So if you have stuff that is really, really strong that's holding it together, it's not going to make a lot of vapor pressure. It's going to make less vapor pressure.
Oh,
right?
okay.
And so this guy technically has two hydrogen bonds, and it also has dispersionary forces, where this guy only has the hydrogen bonds.
Oh, okay.
Okay, so then who's next?
Water.
Okay, who's going to be above water?
Ethanol.
That's right. And then at the highest vapor pressure is going to be diethyl ether. Are you guys with me? Alex, Taylor, because you guys were real quiet.
Yeah.
Yeah. Yeah.
Okay. Okay. So because those forces are kind of like an additive type of situation, the more forces that you have, especially if they're strong forces, the stronger it's going to be. So if I had a molecule, let's say it was okay. So if I had a molecule like this, CH3, CH2, CH2, OH, CH2, OH, CH, OH, CH, OH, CH, OH. Which one is going to have more vapor pressure associated with it?
The CH, the one on the right.
A or B? So you're saying B?
B.
That is correct. Okay. Simple, not too hard.
Mm-mm.
So which one is going to have the highest boiling point?
A? No, B or A? A.
A. That's right. A would have the highest boiling point. Okay. And so does that make sense to you guys? You see how you're piecing it together?
Mm-hmm.
Good. Okay, so we also know that vapor pressure is going to increase with temperature, right? So
Yeah.
as the temperature increases, we know that the vapor pressure is also going to increase. PV equals nRT. Or if we just break it down in terms of the law of kinetic molecules, or the kinetic molecule theory, where, you know, as the molecule gets heated up, it gets faster, it's moving faster, right? And so this graph basically just shows that, right? So you're going to have more molecules escaping into the gas phase as the temperature heats up. Okay, so boiling points. You guys already know what the boiling point is, but specifically, the boiling point is just when the vapor pressure of a liquid increases just enough that it's equal to the external pressure, right? Or external atmospheric pressure. Okay, so normally at sea level, the external atmospheric pressure is about 1 atmosphere. So it's basically that temperature that it's reached where we're at 1 atmosphere, like slightly above 1 atmosphere, and then the vapor pressure is slightly above 1 atmosphere. And so that will be our boiling point. Okay, it's the temperature where we're slightly above that pressure. Does that make sense? Okay, so if I go, let's say 1,000 miles below sea level, where the pressure is a lot more intense, right? We have a lot higher external pressure. What's going to happen to the boiling point?
It's going to increase.
What was that?
It's going to increase.
It's going to increase. That's right. If I go up to the mountains, you know, where we're at a very high altitude and the pressure is very low, what's going to happen there?
It's going
to
to
the boiling point.
decrease.
It's going to decrease. But have you guys read on the back of like cake mix where it says at elevated altitudes, use a temperature of blah, blah, blah. You know, so normally it's like 350 and then it'll drop down to like 250 or something like that. So this is the reason why. It's because of that pressure. So does that make sense?
Yes.
Yeah, no, maybe?
Maybe.
Piece of cake?
No.
No.
It got me a little confused right here at this point.
Okay, so now I'm going to introduce you to the heat of vaporization. We've talked about enthalpy in general, but the heat of vaporization is the amount of energy that it basically takes to convert 1 mole of liquid to gas, okay? And this, the units are typically kilojoules per mole. Occasionally they'll be in something else to make it a little bit easier for you on like an exam or something like that. So just so you know, you want to think about the units, pay attention to the unit. Typically, again, kilojoules per mole, okay? So, let's see. So if we take a look at those same molecules that we just talked about, ethanol, ethylene glycol, oops, and the diethyl ether and water. This is just pressure versus temperature. So you get an idea of the vapor pressure as a function of time. And you can see that, you know, the diethyl ether, as your temperature increases, your vapor pressure increases. And it increases pretty drastically, right? So these really low temperatures, you're getting a lot more vapor pressure that are being generated. The ethanol, as its temperature increases, its vapor pressure increases. But if we do a comparison of the diethyl ether to the ethanol, the water, and then ethylene glycol is even off the chart in this case. And this is assuming that we have 1 atmospheric pressure. Okay, these would be the boiling points of these compounds, right? So that's consistent with what you guys just observed, what you were talking about. Okay. Oops. Okay. So there's a chemical equation called not chemical equation. There is an equation called Clausius-Clapeyron equation. So basically, the Clausius-Clapeyron equation associates vapor pressure to the enthalpy change in temperature, right? So this is just basically a derivation of PV equals nRT, how they came up with this equivalent thing. Okay, so here, your R value is right here. This is the same R value that we use for gases. Only thing, it's been converted to a different unit. So it's joules, moles, Kelvin, instead of atmospheres, liters, moles, Kelvin. Okay. So if we modify this equation, this ln A, So the logarithm of A is basically going to be a constant. And since it's a constant, we can sit there and set the equations equal to each other so that we have one pressure and the second pressure. And if we do the, if we actually do the substitution, we'd basically end up with ln P2 divided by P1 equals delta H vape, where this is the enthalpy of vaporization over the constant R times 1 over T1 minus 1 over T2. Now, if I have these values here, I should be able to calculate the enthalpy associated with water, right? At, or the enthalpy of associated with water going to gas or to steam, okay? So how would I go about doing that using this equation? And knowing that my units here are in Kelvin.
Switch the degrees to Kelvin.
Switch the degrees to Kelvin. And how do I go about doing that?
Add 273.
Right, 273. So then that's 298. $323. Okay. So then it becomes pretty simple. I can just plug it directly into this equation and solve for the delta H vape. So I'll say delta H so I'm actually gonna T1 minus 1 over T2. Oops. P2 over P1. So if I plug in these numbers, so do I have to convert the pressure?
No.
No, I don't. Because the units are going to cancel each other out. Per mole Kelvin over 1 over 298 minus 1 over 325. I mean, sorry, 323. Oops. Times ln 92 divided by 24. Okay, so that's going to equal 1.34. say 290. Oops.
And Dr. Henry, do we have to memorize that equation or will it be given to us?
That is going to be given to you. I'll put it on your. Yeah, so far you have two equations. Okay. So that would be our delta H of enthalpy. Okay, questions, concerns, Cash? Any questions?
No.
Okay. Okay, so now if we sit there and we take a look at the delta H of enthalpy, so you guys remember when we were talking about enthalpy in general, when we're talking about the heat of reactions, thermochemistry, right? And we had mentioned intrinsic functions, right? So I said something about like, it doesn't matter how you get there, it just matters that you get there. So you can take several steps to get to the same point, or you can go directly, right? So if we go from a solid to a gas, which is sublimation, so the delta H of enthalpy is going to be equal to the step from going from solid to a liquid, which is fusion, plus that of the delta H going from a liquid to a gas, which is the heat of vaporization. Okay, and so our delta H sub is going to equal delta H fuse plus delta H vape. Okay, makes sense?
Yes.
Okay, so now when we start talking about heat and cooling curves, heating cooling curves are going to use those transitional states, right? So this is for water, right? So we know that water freezes at 0 degrees Celsius, right? Or we should say ice starts to melt at 0. So anything, as soon as you get slightly above 0, ice will start to melt. So you get a liquid, right? So this line here represents the state, that transition state from going from a solid to a liquid, right? And so at this state, you have both moieties existing. You have your solid and your liquid. As soon as you get beyond that, then you have your liquid state, okay? So if we're going from 10 degrees all the way up to 110 degrees, we would have to take in consideration the phase changes that are going to be there as well. So this guy would be, that line represents Q equals, and that's Q of fusion, so which is basically melting, equals N. N means the number of moles times delta H fusion. This point going from -10 to 10 is going to be what we had done prior, where Q ice equals MC ice, where C is the specific heat. Do you guys remember specific heat? The specific heat capacity?
3.18 or 3.81 or something like that.
Actually, for solid, going from a solid to a, well, for ice, it's going to be 2.09. You're thinking about 4.184 for water, for the liquid phase, yeah.
Oh, yes. I was way off.
Yep. Okay, and so where that delta T represents going from -10 to 0, then here, we're going to have Q equals to the specific heat of water times delta T, where we're going from 0 to 100 degrees. And then this guy, we're going to have Q equals N, and that's Q vape, N delta H vape. And then this last part would just be Q gas equals MC gas delta T, where delta T is going to be from 100 to 110. Okay, so typically what you're doing, you're calculating all of the energy it takes to go from -10 to 10 degrees. Now this could be, you can also go from 110 and cool down to -10. In that case, you know those values are going to be negative. In that case, you're going to just going to be subtracting everything. Does that make sense? So in other words, that's going to be the energy that's going to be released from that system, removed from that system. Okay, this is the energy that you'd have to put in to get that to happen. Okay, knowing that, how would you set up this problem? All this stuff. Hold on 1 second, and I'll give you a chance to sit there and figure it out. I'm going to give you a quick hint, though. Draw the curve. It makes it so much easier. Okay, so you guys work on my board. I'll be right back.
Did you guys get any of that?
Kind of.
Yeah, same here.
Sorry about that. Postmates was delivered to the wrong house.
Okay, this might be a dumb question, but the M in MCAT is mass, right?
That is correct. Yep.
Okay.
So what C are you going to use in this case?
I wasn't sure. Would you go like liquid?
Would it be the
So-
solid state?
Solid state. That's right. So we'd be using this one. So you'd multiply it times the multiplied times the 2.09 joules per degree Celsius grams. And so that takes care of this guy, right? So it'll be your final temperature, which will be 0 degrees minus 15 degrees. So it'll be, minus 15 degrees. So in other words, times 15, right? And we get that because we know that 0 minus 15 would just be 15, right? Okay, so then that takes care of the ice, that ice phase part of, or the going up to the ice phase, right? Now, what about that transition as we go into the liquid phase? How do we account for that? That part there. Do we use that, or do we use
For the fusion one?
the fusion one? That's right. So we use the heat of fusion, which is here, right? And that's in moles. So we'd have to convert our grams to moles of water. So that's Q equals, how do I convert 135 grams of water to moles of water?
By dividing it by the mass or the molecular weight.
Okay, so we know water is 18 grams per mole. Okay. And then we multiply that directly by our delta H of fusion, which is times 6.01 kJ per mole. Moles are going to cancel out, and we're left with just kJ. Now somebody's plugging these in, right? So then we're going to go from here. Oops. I'm going to move that over, all of that over. Okay, so if we're going from here, that Q is going to be what? If this represented the transition, that represents the line here. Now, what are we going to use to represent going from 0 degrees to 100 degrees?
Like, what do you mean?
What equation are we going to use that is going to allow us to calculate the energy that it takes to go from 0 degrees to 100 degrees? Because we put in a different color.
Would it be Q equals N delta H?
It wouldn't be Q equals N delta H. Q equals N delta H. Right there. That's what that is.
Oh, okay.
Would we do the vaporization one?
What was that?
The vaporization?
Is it vaporization? Right? Because vaporization represents us transitioning, right? So this line here represents a transition. So we're going from minus 15 degrees. So if we're starting at minus 15 degrees, what state are we in?
Solid.
Solid?
We're solid. Okay, when we get to 0, we transition from a solid to a liquid. As soon as we get above 0, then we're what?
Liquid.
We're a liquid. So then how do I represent going from a 0-degree liquid all the way up to a 100-degree liquid? Q is going to equal to what? What did I do for going from a block of ice to the point where I transition to ice?
MC
MCAT.
delta T.
So I'm going to use MCAT, right? MC delta T. Okay, so in this case, I'm still using the same value for my M, which is 135. I'm using the liquid state. And then I'm multiplying it by the change in temperature, which is 100 minus 0, which is just 100. Okay. So then at 100 degrees, what happens?
It vaporizes.
It becomes a vapor, right? So it vaporizes. So we have to get that change in transition. So we're going from a liquid to a vapor. So how do I calculate that?
The heat of evaporation.
That's right. So it's delta H vape times the number of moles. Oops. Okay. And so then that's going to equal 7.5 moles times the heat of vaporization, 44.01.
How'd you get 7.5 moles?
135 divided by 18.
Oh,
Moles are going to cancel out. And we're left with times 1. So 4 sig figs. So then that'll be KJ per mole. Okay, and then we're going with this vaporization all the way up to the very top. Let me move this out of the way. Okay, so how do I calculate this from going from 100 to 120?
MC delta T.
Okay, so then that's going to be 135 grams times, in this case, the gas state, 1.84 joules per centimeters, joules per Celsius grams. So grams are going to cancel out. Change in temperature, we're going from 120 or minus 100, running out of room. So I have Q is going to be equal to 135 times 1.84 times 20. 4.97 kilojoules. And this guy was 135 times 4.14. Oops. Times 100. So this guy would be, oops.
So you only use the equation Q equals N delta H when it's transitioning to a different phase or different state?
That's right. You only use that one when it's transitioning from phases. So if you're going from a solid to a liquid, that transition, that straight line, or this one up here, that straight line right there.
Okay.
Excuse me one second. Sorry about that. Food being delivered. This time the right place and the right food. Okay. So now we want to calculate the total going from that minus 15 all the way up to the 120. So we're going to add them all together. So if we do that, oops. Sorry. Taylor, what did you get for this last one? Or did you do it?
I got 4232.25.
4 point.
Oh no, I got 4232.25. 4,232.
Okay. So then it'll be 4.2, right? 4.2.
4 kilojoules.
Yep. KJ. Okay, so then we just add them all together. So we'll have Q total. It's going to be equal to that Q ice plus Q fusion plus Q liquid plus Q vape plus Q gas. So then Q total, I love putting these on the test. Is going to equal 4.23 kJ plus this guy is equal to 1.5 times 6.1, 45.1 kJ plus 56.5 kJ. This transition is plus 300.1 kJ. And plus down here. .97 kJ. So that's going to equal 0.9 kJ. Okay. Piece of cake.
Yes.
Yeah, just seems like a lot of work.
Yeah.
After you erase this, could you rewrite the different, like the QMC ice fusion? Yeah.
Yeah. So Q total is going to equal Q ice plus Q fuse plus Q liquid plus Q vape plus Q gas. Q ice equals the mass times the specific heat capacity of ice or the solid times delta T, and that's up to the point where the ice transitions, right?
Mhm.
Q fuse equals the number of moles times delta H of fusion. So that represents the transition from solid to liquid. Q liquid equals MC liquid delta T. Q vape equals number of moles times delta H vape. So that's the heat of vaporization. And then Q gas equals MC gas delta T. Okay. Questions? Concerns? Cash? No questions?
Not right now.
Okay. Did everybody get that down so I can clear? Okay. Okay, so this is called a phase diagram. And so it basically shows us where the phase changes occur. And it also lets us know the temperature of each of those occurrence. Okay, so or where the transitions are going to occur at temperature versus pressure. Okay, so if we take a look here, solid, gas, and liquid, we have what we call the triple point. The triple point is where all three phases exist at that particular temperature and pressure. Okay, this here represents the line that goes from sublimation. So you're going from a gas to a solid, so that's deposition, or a solid to a gas, that's sublimation. This line here represents the transition between vapor and condensation, vaporization and condensation. And so again, gas to a liquid, liquid to a gas. This here represents freezing and melting. Okay, so your critical point is the point where you kind of lose that line, that very distinct line between gas and liquid. And so you kind of get something that's an intermediate between the two, right? So it's less dense than liquid, but it's more dense than gas. It's less viscous than liquid, but it's less dense than gas. I mean, less viscous than gas. Okay, and so it's able to dissolve things and things to that extent. Okay, and so we'll talk a little bit more about that on Wednesday. Okay, so are there any questions? Concerns? Credit? Cash?
Debit.
You said we're gonna have a lab on Wednesday, right? Or two
Yes,
labs?
it's going to be 2 labs because the first lab is just you're going to break your glow sticks, you're going to put it in ice, and you're going to keep it in a ice, and you're going to measure the temperature, making sure that it stays relatively constant. And then you're going to have one at room temperature, and then you're going to have one with warm water. That's also going to be tried to be maintained at a constant temperature. Okay, and then you're going to look at it for, you know, the first 15 minutes, you know, you're going to take a look at it. So you're going to take a look at it when you first do it and take the intensity, then you're going to measure that intensity afterwards, and then you're going to measure that intensity afterwards. And so you're going to just kind of keep track of the intensity of it. So you're going to take pictures of it at different time points. Okay.
Oh,
And
okay.
so, and then your other lab, I have to look at what it is. It'll probably be something like what is it called? An acid-base type of lab. But a relatively fast one. Okay. Questions, concerns, cash, credit? Okay, I have nothing else. I guess I'll see you guys on Wednesday.